We will now spend some time discussing the more complicated identification techniques, which I have referred to in previous movies. When you want to identify something, we have to determine what characteristics distinguish it. If you're looking at two different objects and you want to know if they're similar, then there are a number of things that you can do, just that you do without even thinking about it. You look at their shape and their size. If one is bigger than the other, then that may mean that they're different. It may mean that they're basically the same, only one is larger. You look at color. Color, of course, is determined by the wavelength of light. And we see these different wavelengths of light, and we were taught from our childhood that a certain wavelength or group of wavelengths is red, another group is yellow, blue, etc., etc. And so color is a nice distinguishing factor in much of what we do. It turns out that we only see a very small amount of the wavelengths that are actually out there. We call it the electromagnetic spectrum. It starts with the very, very short, very, very high energy wavelengths down in the X-ray range and goes up into ultraviolet, and then into the narrow band that we see, which we call visible wavelengths. And beyond the longer and less energetic, beyond our ability to see with our eyes, is the infrared, and ultimately out at the very long, very low energy wavelengths, like radio waves. So we can see a lot of colors. Our eyes are very, very efficient, excellent at distinguishing about 1,000, maybe a couple hundred more, maybe 1,400 different colors. And so if two things are color-wise indistinguishable, that's a good indication that they have similarities other than just how they reflect light, and we'd have to do more things. But we found that some of the other wavelengths of light are also very distinguishing. A lot of the infrared radiation, that is the wavelengths just above the visible spectrum, reflect and absorb light in a very efficient and high variety. So we have designed instruments to measure the absorption and transmission and reflection of light for many, many different wavelengths. We haven't designed one instrument that will look at all of them. So we start with the electron range, or the X-ray range, and we have instruments that will measure the absorption at various wavelengths in that range. We have ultraviolet spectrophotometers that measure the range of wavelengths just shorter and more energetic than what we can see. And we have spectrophotometers that will measure ultraviolet and visible. And then we have infrared spectrophotometers to measure the range just above what we can see. Some of these are better than others, and it depends upon what kind of material we're testing. But spectrophotometers are excellent at distinguishing drugs, particularly in the infrared range. Infrared spectrophotometers are among the most distinguishing and best identification tools that we have for identification of drugs or other mostly organic compounds. But by the way, organic in this term is the chemist's organic. It doesn't mean that the chemicals were raised without pesticides. Nowadays we see organic this and organic that in the grocery store, and we're talking about organic, meaning as a chemist contains carbon. That's the definition of a chemist's definition of organic. So I will get some pictures of infrared spectra, and we'll talk just a little bit about them and what they do. Before we look at some spectra, let me mention that the textbook contains a very nice explanation of spectrophotometers, and I will expect that you spend some time reading that section. It will maybe be clearer, or at least give you an additional insight into spectrophotometers and how they work, and some of the spectra that I will show you are taken directly from the book. Here is a electromagnetic infrared spectrum of the compound called vanillin. If you look at the left side, you will see that the vertical axis measures the percent transmission, that is the percentage of the light that is passed on through the material. The larger the peak, the less transmission occurs. So right in the area of in the area of the horizontal line, you'll see 4,000, 3,000 on down to in the 600, 700, 800 range, and so that is the wavelength, going from 4,000 being the longest that it measures, down to the right being the shorter ones. So what it does is it measures the amount of light that passes through the vanillin molecule at these wavelengths and how much is transmitted. We can also measure how much is absorbed, and some spectrophotometers allow you to measure how much is reflected. But this one is for the transmission, or passing the light that passes through. You can see this is a very complicated spectrum, lots of peaks, some of them very long, some of them very short, but each of those peaks represents an interaction with vanillin, and the likelihood of another molecule producing exactly the same spectrum is very, very remote. So if you have two infrared spectra that match, then you can be pretty confident that we're looking at the same compound. So these instruments are used all the time in drug identification. We have complex instruments that computerize the peaks and memorize them as you will, or store them, so that you can call up the database and ask it to find the nearest one or the closest one, and it would find vanillin, and it would show it to you, and you could overlay the vanillin spectrum with this spectrum, and they would be the same. you would say, okay, these two specimens are vanillin. Now I'll show you another spectrum of a different compound for comparison. This is a spectrum of heroin. It is considerably different from the spectrum of vanillin. Ultraviolet spectrophotometers are also used in crime laboratories, but their spectra are far less complicated, and they are best used for determining the quantity rather than the identification of a complex molecule. We also have spectrophotometers which will read in the X-ray range, and if you recall the firearms lecture, when we were talking about identifying gunshot residue and determining the chemical makeup of gunshot residue particles, we used X-ray analysis. They have an X-ray analyzer attached to this scanning electron microscope, which allows them to determine what the particle is made of, and if it's barium, antimony, and lead, then it's almost certainly a gunshot residue particle. There are also instruments that measure in the wavelengths somewhat longer than the regular infrared, and they are valuable, and depending on the application, we may gain information from them that we don't get from the others. So spectrophotometry is a broad science, and chemists can specialize in spectrophotometry or specialize in a particular kind of spectrophotometer for their whole career. We don't intend to do that. We just want you to know a little bit about infrared, and be sure to read that portion of the chapter in your book, because it is well written, and you'll gain a better understanding of the process. The next topic for discussion is chromatography. The name chromatography sounds like it ought to have something to do with color. In actuality, chromatography is a method of separating compounds. It was invented, if you will, by a Russian botanist who was studying pigments in leaves, and so he named it after the fact that he was studying pigments, but it really, in our application, has nothing to do with pigments. Chromatography is a way to separate things. If you have a mixture of compounds, it's often necessary to separate them in order to have a pure compound for identification. And as you will see as we go along, chromatography also allows you to identify each compound as it is separated. To give you a little understanding of the process, I have an analogy that may prove helpful. Assume you had a mixture of sand and BBs from a BB gun and marbles, and you wanted to separate them. You could put them in screens that would separate one of them, or a screen that was slightly larger than the sand, but smaller than the BBs, and you could get the sand out. But another way, certainly more efficient way, would be what we call column chromatography. So you would get a tube and fill the tube with baseballs. Then you would pour your mixture of sand and BBs and marbles on the top of that, and then wash the tube with water, a continuous stream of water going through. And you can imagine that the sand particles, being very small, would have no trouble finding enough spaces between the baseballs. The sand particles would go on through. The BBs, being a little bit larger, would have to go through a little bit slower, because they would have to find channels that were large enough for the BBs to work their way down through. Finally, the marbles, they wouldn't have very many places where the marbles could go through, so it might take them a long time. Maybe they wouldn't even make it. Maybe they'd get stuck. But in any event, you would have separated the particles. If you'd collected the initial rush of water through there, you would have gotten most of the sand. And if you'd got the second rush of BBs, then you would have your BBs separated from the sand, and then the marbles would come through last. So that's the general idea of chromatography. And in this analogy, it's not a really good one because all it takes into consideration is the size. In actual chromatography, we also have to consider attractions. Chemical compounds have attractions for each other. Some are attracted very strongly. Some of them are attracted less strongly. Some of them are actually repelled. And so attractions, if there was some attraction from the baseball to the sand, it wouldn't let the sand come through. There isn't, so in that case we're only dealing with the physical size. But in real chromatography we have the size and shape of the molecule and the attraction that the molecule has for the stationary phase, baseballs being the stationary phase, because they don't go anywhere. So that's column chromatography. We used to get a lot of LSD, and it would be in a pill or some preparation, and we'd want to identify the LSD separately. So we would have a column that would contain a separating material, and we would dump we'd dissolve the LSD, and then we'd pour it into the column, and the LSD would come out, and we could easily tell when the LSD was coming out because it would be a pure liquid, and our stationary phase would stop the dye, which was what we were trying to get rid of, was the dye. And so when the first amount of liquid came through the column, we'd capture that, and the dye and the other impurities would stay in the column, and we'd just evaporate the liquid, and the LSD would be relatively purified. So that was an application that we had in our crime laboratory. After the Russian botanist, whose name I can't pronounce, there have been lots of advances in chromatography. So now there's still uses for column chromatography, but we've developed a number of other ways to use the general principle of chromatographic separation. One is to just take a piece of paper, usually something like filter paper, something that's uniform and well made, and put a few spots or a spot of whatever material we want to separate. We dissolve it in a solvent and drop a spot or two on the paper, keeping track of where on the paper we put it, and then we would take that paper and put it in a tank that had our movable phase, the equivalent of the water going down the column of baseballs. So that column, that solvent would gradually creep up the paper and get it wet, just like if you put a paper towel corner in the water, pretty soon you see it's kind of creeping up and getting the rest of the towel wet. So eventually the compounds would be separated because some of them would be bigger or smaller than the spaces between the paper particles. Some of them would have an attraction primarily from the water in the paper. So water is a pretty good separator, and so paper chromatography is good. The next advance was what's called thin layer chromatography. In thin layer chromatography, you take a plate, usually glass, but can be metal, but usually not metal because metal reacts with things. So you take a plate and coat it with something that you want to be your stationary phase. and so you have a thin coating on the glass plate. We have several applications for this thin layer chromatography, one of which I will demonstrate now. So here is a glass plate. It has a white coating on it. The coating is called silica gel. That happens to be a good separating material for the samples that we're going to be using. And it's divided up into channels with spaces in between, and that makes it easier to keep track. If you put several samples on there, then you can keep track of which one is which a little bit easier. So at the bottom of this plate, I have put 4 different samples of ink. 2 of them are the same pen. 2 of them are different pens. If we had a sample of ink and we wanted to determine if it was written by a particular pen, we could use thin layer chromatography. So this will demonstrate that each of those black spots then represents a little spot of black ink. And I've placed the plate in a jar to begin the process. The jar has a separating solvent in the bottom of it. Okay, at this point the solvent has climbed just a short distance up the plate. You can see the solvent line at the top of the black spots. You can see the first on the left has climbed up quite a bit, and if you look very carefully, you'll see the beginning of separation down near the bottom of that black spot. It's a little bit purple. The second spot isn't very soluble in the solvent and isn't moving much, and you don't see any separation. The third one looks pretty close to the first one. The fourth one, most of the black is still where it started, but you see an orange band that is moving away. So we're beginning to see separation. And actually, I think at this point, if you had to guess, you would guess right that the similar pens are 1 and 3. But we'll let it go a little bit further and get a little bit more separation, which will make it a little more obvious. So now we see quite a bit of separation. The solvent front has gone quite a ways up the plate, and the first one and the third one, you can see how there's, even though the ink started out black, there's lots of other colors in there, some pinks and some reds and some purples. But the first one and the third one are basically the same. They've separated out, and the spots have traveled the same distance on both plates. The fourth one is still has that orange, but doesn't look like the first 2. So assume we had a sample of heroin that was mixed with sugars and various other substances. We could put a spot of heroin, known heroin, on the plate, and a sample of the unknown, still to be identified powder. And the heroin from the known would travel up the plate, and the heroin from the suspect sample would travel the same speed, and they would end up both equally having equally traveled the same distance. And we could say, well, they both traveled the same distance, and so in all likelihood this is heroin. So we would have identified the heroin in the sample. Thin layer chromatography has applications in the crime laboratory. We use it if we have a sample which we think is marijuana, but we can't see the cystolytic hairs, and so we then do the Ducanoid test, and then we do a thin layer plate similar to the one I just showed you, and the components of marijuana will separate out, and if we've got a known sample next to it, then we have several spots that travel the same distance, and and change the same colors when we spray a dye on them, and that's a really good and powerful way of identifying marijuana residue. Certainly a lot cheaper and faster than some analytical techniques that we're going to discuss next. So more sophisticated way of doing chromatography is, instead of using a glass plate with a coating on it, we use a tube, a very small tube. Some of them are only a few millimeters, some of them even less than a millimeter in diameter, but they're long, up to 150 meters long. And the inside of the tube is coated with the separating material, which would be the equivalent of silica gel. And there's lots of coating materials. You can purchase these tubes pre-made, and you buy one that has the coating that works best for the substance or type of substances that you're trying to identify. In any event, so you have this long tube, and you put it in an oven and hook both ends to the inside of the oven, such that you can inject directly into one end of the tube. And you can control the temperature, a tenth of a degree Celsius, and you can heat them up to whatever temperature works best. Temperature is another factor in how fast things would go through the tube, in addition to what we've already talked about, the size and shape of the molecules and the attractions they have for the coatings or the stationary phase. Then we take the material we're trying to identify, dissolve it in a liquid, and inject a small amount of the liquid into the end of the tube. The tube has a continuous flow of a gas that usually it's helium, because helium doesn't react with things, but it can have other gases that this continuous flow of helium will push the sample that we've injected through the column, and it's hot enough that it turns the sample that we injected into a gas. So it's a gas, and it pushes the other gas through, and the lining of the column, which is, we use the word column rather than tube, but I use tube because I thought you'd be more familiar with it. But in any event, pushes it through the column, and we put a detector on the end of the column, which detects how long it takes a sample to come out. So it starts the timer, and as soon as something goes through the detector, it's recorded as, okay, something just came out, something other than the helium just came out. And so if you have several compounds, they'll come out at different times, which we call retention times. And the retention time of a compound is what we measure. So we can say, well, at 130 degrees Celsius, amphetamines come out in 2.2 minutes. So if we have an unknown and we dissolve it in a liquid and inject it into the chromatograph, and it takes 2.2 minutes to come out, then that's a pretty good sign that it's amphetamine. It's quite a nice technique. It's pretty fast, and you can actually automate it so that you can have the instrument do many samples in an automated fashion. When we do blood alcohols, for example, we put the blood in a little vial, and we cap the vial with a rubber stopper, thin rubber stopper, and we put that in a cassette similar to what we used to use when we used to use slides in the old slides. The slide cassettes, the round ones that would sit on the top of your slide projector. I hope some of you remember that. In any event, that's sort of a cassette goes on the top of the gas chromatograph, and you start the instrument, and it puts a needle down into the tube, sucks up some of the air in the tube. Doesn't need any of the blood. Just the alcohol will have a certain enough gas. There'll be enough alcohol in the gas that the needle will suck up air, and then it'll inject it directly into the gas chromatograph, and then it will rinse itself and run, and then it'll run a blank, and then it'll run the next sample, and you can put 30 or 40 samples in there and start the instrument and go to lunch. When you come back, you have a computer printout of all the blood alcohol levels of all the samples. So that's a nice thing, very accurate, very reliable, been around quite a long time, and not terribly expensive. You can buy a nice gas chromatograph for maybe $20,000, which may sound like a lot to you, but when you consider how much a police car costs, and every police officer has a car, so every lab has a gas chromatograph, or more than one. So here's a picture of the front of one of our gas chromatographs. You can see it's got lots of buttons and dials, and the modern ones have, they're computer operated, and this was an old timer, but it was a very good one. So that's what they look like from the out. And this shows a syringe being used to inject a sample. You can see it's a very small syringe, pretty long needle, but we can inject very small samples, oftentimes a tenth of a milliliter, or even less than that. So the samples that you inject into a gas chromatograph are about the size of the dot you would make with a ballpoint pen. So they're extremely sensitive and require very little sample. So that's how we inject it in. So this is a picture inside the oven with the door open. This particular gas chromatograph has two columns. And if you look at the bottom right side of the oven, you'll see the two columns. They're very small, as you can see, and quite long. So that's the oven, and as I said before, we have very tight control of the temperature in the oven. Here is a copy of a diagram from your book showing the essential parts of a gas chromatograph. And the last part of that on the right is a graph that is generated by the chromatograph, showing each of those peaks would be a separate compound that's been separated out. This shows a chart of several barbiturates, which are closely related compounds, which were injected into gas chromatograph. The bottom line is divided into minutes, as you can see. It separated the barbiturates quite nicely, and this is a good example of how gas chromatography is used in the crime lab. Chromatography is a very highly utilized technique in laboratories, but as we have looked at chromatography, we've used gravity as a way to move the sample, and also pressurized gas to move the sample. Another mechanism is electrical current, direct current. As you know, positive charges are attracted by negative charges. So if you have a sample that has a charge on the molecules, which most biological molecules, proteins, etc., have, then you can arrange your system such that there is a current flowing across, which will cause the negatively charged molecules to move to the positive side, and the higher the charge, the faster they will move. And the larger they are, the slower they will move. So that is the way we separate things like DNA and other biological samples. That technique is called electrophoresis, and we may discuss that when we get into the DNA section of this class. Chromatography, particularly gas chromatography, is a very excellent technique and is utilized for many, many things. It also has its limitations. Compounds that are very closely related chemically may not separate very well, so you may have difficulty determining whether a particular sample is one compound or more than one compound. So many experts say that you should do some additional testing, and we will go into the next more sophisticated technique in the next segment. One of the characteristics of molecules is their molecular weight. Different compounds have different molecular weights based on the atomic weights of their individual atoms. Water, for example, has 2 hydrogen atoms and 1 oxygen atom, H2O. Hydrogen has an atomic weight of 1, oxygen has an atomic weight of 16. We have 2 hydrogens and 1 oxygen, so we have 16 plus 2, which is 18. So the molecular weight of water is 18. And that's a characteristic that we can calculate for virtually any compound as long as we know the formula for that compound. So if we knew the molecular weight of the substance we were trying to identify, that would be a helpful characteristic to use. It would be like in a human, if we knew the color of your eyes, then that would separate you from those whose eyes have a different color. It would not, though, of course, individually identify you. It turns out that another characteristic of molecules is that they are capable of breaking up into fragments. If you bombard a molecule with some sort of atomic particle, you may be able to break the molecule into pieces. And a specific molecule, when fragmented, will fragment in the same way every time. So now, instead of just having the molecular weight, if we could calculate the molecular weight of each of those fragments, that would give us a much more accurate identification. So that concept has been incorporated into a technique called mass spectrometry, or mass spec. The mass spec is an instrument that's only been around for about 60 or 70 years, so it's relatively new, but it's come a long ways. And when I first started in this business, a laboratory that had a mass spec was really something to brag about. Now every laboratory will have a mass spec or more than one. And of course, with that has come a decrease in the cost and an increase in the usability. One of the problems with mass spectrometers is that you need a pure compound in order for the results to be meaningful. If you inject a mixed sample, such as these barbiturates we saw in the gas chromatograph, then it will give you the result of the fragmentation of all of them, and you wouldn't be able to know which one is represented by which number. So we need to inject pure compounds into the mass spectrometer. And minds wiser than mine determined that one of the ways that you could inject a pure sample is to send it through the gas chromatograph and have the compounds separated into pure samples. So they attach a gas chromatograph to a mass spectrometer, inject into the gas chromatograph. You get a retention time, which is a pretty good identification feature on its own. Plus, you then get the fragmentation pattern, which is very, very close to being unique and individual for a specific compound. Here is the mass spectrum of heroin. The peaks with the little lines represent fragments of the heroin molecule. The numbers represent the mass, actually the mass to charge ratio, but since the charge of almost all of them is 1, we can call it the mass. So each one of those mass fragments is identified in the mass spectrometer, and you can see there's a large number of fragments as there is in any somewhat complicated molecule. So this is a really really specific way of identifying compounds. It is used in drug identification. It is used in numerous other applications in which specific identification is required. For example, in the sports world, we now have lots of athletes who are attempting to improve their abilities by taking steroids. And steroids are a very complicated molecule, and there are a lot of different steroids. So mass spectrometry is used to identify if an athlete has taken a substance which is prohibited by the athletic association. Now most laboratories have a GC mass spec. GC means gas chromatograph, and mass spec is mass spectrometry. So a GC mass spec is standard laboratory equipment in crime laboratories. They are relatively expensive. A really fine one can be $500,000. Those kind aren't usually in crime labs, but they have benchtop or tabletop instruments nowadays that are available for $120,000, $150,000, and they are just the workhorse of the drug identification section, and are used in other applications as well, which I will mention as we talk about trace evidence and toxicology. As you will recall, that chart, the results are numerical and are therefore easily digitized. So now we have computer databases which show the fragmentation patterns of virtually any compound that you want to have, and you can build your own. So now the chemist injects into the gas chromatograph, it goes through the mass spec, we get the retention time, we get the fragmentation pattern, and we ask the computer on the mass spec to search for a similar spectrum and show that spectrum, which we then can overlay over our suspected sample spectrum and determine if the sample is what we think it is or what the computer has brought up. It is absolutely essential nowadays for a modern crime laboratory to have available a GC mass spec. This completes our discussion of instrumentation and techniques for identification of drugs, with the exception of a technique called microcrystalline microcrystalline tests. Microcrystalline tests do not require a powerful and expensive instrument. They use a microscope, regular, ordinary light microscope, some of which are polarized, some of which are not. But the principle here is that when you dissolve something in a liquid, it may eventually crystallize out. Maybe some of you have gone out to the Great Salt Lake and found salt crystals. That is salt that is crystallized out of the water in the lake. So depending on the solvent and depending on the material in question, crystals are formed, and each compound will form a crystal that may have a specific color or a specific shape or both. And so you dissolve the very, very small sample in a liquid and observe the formation of the crystal under the microscope. And if you have experience and have been trained in what a particular crystal from a particular substance looks like, you can identify it. Some modern chemists look down on microcrystalline tests because they don't use a computer and they don't use an instrument, and they don't cost lots and lots of money, and they don't result in a computer printout. But studies have shown that a well-trained analyst can reliably identify particularly drugs based on their crystal formation. I think I have a picture of cocaine crystals, which I will put up. Here's a photograph through the microscope of a cocaine crystals dissolved in gold bromide. They form little stars, four-pointed stars, not scars. In the bottom right-hand corner, you can see one crystal that's slightly different in color. The one next to it is gold, and the one in the bottom right-hand corner is kind of a blue. It turns out if you examine these crystals under polarized light, that they are blue in one orientation and gold in the other orientation, depending on how the crystal is formed. And so if you rotate the microscope slide, the gold ones turn blue and the blue ones turn gold. And I often comment that you don't need to snort cocaine. You can just look at it under the polarized microscope. And so you've now had an introduction to numerous ways of identifying drugs. What you need is a scheme that takes advantage of all the techniques, and ultimately you arrive at a identification which is in your mind or in the protocol of your laboratory a satisfactory identification. You should start by looking at the sample. Is it a white powder? Is it a brown powder? Is it a dark black, thick, tar-like powder? Is it a pill? And so you may then just do a gross examination with your eyes, and oftentimes that will help you to arrive at a preliminary idea of what it might be. You will take into consideration other factors such as packaging and so forth. Then you decide, well, this looks like it might be cocaine. So then the first thing you would do is the cobalt thiocyanate test for cocaine. If it turned blue, then okay, we'll proceed to the next step. If it doesn't turn blue, then you have to revise your thinking and start over with another one. Maybe it's amphetamine, maybe it's nothing, maybe it's not controlled. But if it is blue and you think it's cocaine, then the next thing would probably be to dissolve a sample and inject it into the GC mass spec. That's skipping a few things. In the case of cocaine, we probably wouldn't do thin layer or paper chromatography or column chromatography, but the GC mass spec would give us an answer, and so that would be the end of the game. So that's what we would do, that kind of a process for whatever sample it came in, and ultimately we should arrive at a conclusion, not just based on the mass spec, but based on the combination of factors, none of which should be eliminated. We should take our time, use what we have available, and get the results that lead us to the next step, and ultimately make a decision.